Welcome back, students. We have two optional topics left. Section 3, Monotone Sequence Theorem, is one, and Section 4, Limit and Convergence, is the other. Section 3 is going to be a little easier. Monotone Sequence Theorem is related to one of the main axioms of real number system. The real number system has three main properties. First property is the algebraic property, and those related to the algebraic rules related to addition and multiplication, kind of like associativity, commutativity, distributivity, additive identities, multiplicative identities, inverses, subtraction and division, things like those. The second axiom is order property, which is related to inequality. Any pair of real numbers can be compared. One has to be strictly less, or those two are the same. Consequently, any real number can be assigned to a point in a line, as a matter of fact. For that reason, people say this real number system is linearly ordered. And the third axiom says the opposite. Any point in a line can be assigned to a real number. And that's not easy to see. One way to see that is to use decimal expansion. And that kind of thing is going to be discussed here. Monotone sequence theorem by itself is very benign. It goes like this. A bounded monotone sequence converges. For example, if you have a increasing sequence that goes up and up and up, if it is unbounded, then it'll go up to infinity, yes. But if it is bounded, now it's increasing, so it cannot come back down. In that case, it'll have to stop somewhere. Consequently, we have a convergence. The same goes to decreasing sequence. That's how we can understand monotone sequence theorem, and that's how I explained it in section 1, sequences of this notebook. And that's mostly sufficient for, well, almost everything we do in Calculus 2. But in order to be perfect, let's talk about a little bit more. Well, let's begin with the concept of boundedness. Okay, let's begin. We say a certain non-empty subset of the set of real number is bounded above if there exists a certain real number u, which we call an upper bound, such that every element of that set A is less than or equal to that u. So every element of A, which we write as small a, lowercase a, is less than or equal to that u. If that real number u exists, then we say A is bounded above. Likewise, we define the other one. We say A is bounded below if there exists a certain real number L, such that every element of that set A is greater than or equal to that set, that number L, which we call lower bound. Here's a visualization, as a matter of fact. The blue part represents the set A in this example here. As you can see, the set A consists of, well, a couple of intervals. We have an unbounded interval on the left-hand side and some isolated points, and then we have an open interval. Any point in the right-hand side, like u1 and u2, is going to be an upper bound. We have two upper bounds here, but of course there are infinitely many more. Now, among those infinitely many upper bounds, we have one particular upper bound that is most interesting, the smallest one. And here's a visualization of that, as a matter of fact. We are looking at the same set. Let me expand this picture too, so that you can see this thing just as easily as before. And u1 and u2 are upper bounds, yes, but there are many more. As a matter of fact, this red interval in the right-hand side represents the set of all upper bounds. And that set has the smallest element, s. And that is called the least upper bound. Let's go back to the original picture here. This The second interval here, which is in the right-hand side, is an open interval. So this set A, the capital A, was defined using a strict inequality. However, the definition of the upper bound was defined through a semi-inequality. So the smallest element for upper bounds always exists. And that is S in this particular example here. And the least upper bound, which always exists, is often referred to supremum. And the greatest lower bound, which always exists, is often called infimum. Excuse me, did I say they always exist? I take it back. Excuse me. Any subset that is bounded above has the least upper bound. If it is unbounded, then that's a different story. In that case, we have to say the least upper bound is an infinity, and infinity is not a real number, so you can say it does not have least upper bound. Same goes to the greatest lower bound. If the set is bounded below, then the greatest lower bound always exists. Infimum always exists. But if it is unbounded, then that's a different story. And this blue set here, the set A, as you can see in this picture and that picture, this set A, this particular case, is unbounded below. So the greatest lower bound in this case is going to be negative infinity, which is not a real number. Well, let's look at some more examples here. Let's see, example 3.4. Interval 0 to 1. Half open, half closed interval 0 to 1 has the minimum 0. That's the smallest element. So that is the greatest lower bound. As a matter of fact, what is the set of all lower bounds? That's negative infinity to 0. Actually, and that is going to be negative infinity to negative infinity to 0. Something is wrong with my internet connection. Okay, now it looks okay. So the greatest lower bound is 0. And I'm not going to prove it here, but you can always prove that. You can prove that if minimum exists, then that's always the greatest lower bound. And if the maximum exists, then that's always the least upper bound. The minimum and maximum do not always exist, as you can see in this picture, in the second example here. Interval 0, 1, this half closed, half open interval has no maximum. 1 is the only candidate, but that's not part of this set, so it has no maximum. However, it does have the least upper bound, and that's 1. How about interval 0 to infinity? That's unbounded, so the supremum, least upper bound, is infinity. But infinity is not really a part of the real number system, so it is equivalent to say the supremum does not exist. And let's apply that to sequences. We say a sequence is bounded above if, well, an upper bound exists. There exists a certain real number m, so that every an is less than or equal to m. Similarly, bounded below if there exists certain m, such that every an is greater than or equal to m. I could have used u and l, but I refrained because using u for upper bound is okay. Using l for lower bound is not good because l looks like limit. And I don't want to have any confusion here. Now, here is the definition of the monotone sequence. Increasing sequence when the next element is always greater than or equal. Decreasing sequence when the next element is always less than or equal. Again, well, that's pretty generic. Now, here we go. Monotone sequence theorem. A bounded increasing sequence converges to its least upper bound. So not just convergence, but where does it converge? or to which real number does it converge? Well, that has to be answered. And the answer is the least upper bound, or supremum, for increasing case, or greatest lower bound, or infimum for decreasing case. The proof is, well, we cannot discuss proof for any kind of convergence or limit here because that's a whole lot different story. We're going to talk about it in a separate video, section 4 of this notebook. Now let's talk about some corollaries. We talked about sequences, increasing and decreasing sequences. What if we consider, what if we consider series? Well, if we have non-negative series, then the sequence of partial sums must be increasing because we are adding non-negative numbers. Consequently, any bounded non-negative series is equivalent to any bounded sequence of partial sums. Any bounded increasing sequence of partial sums, So we have to have a convergence. Well, here is a brief proof. Sn minus Sn minus 1 is an that's greater than or equal to 0 because every element is non-negative. Consequently, Sn minus 1 is less than Sn, so next term is always greater, where Sn is the partial sum, as you remember. Now, here's a second corollary, which is very, very powerful and interesting. The decimal expansion is valid in the set of real number system. That's very interesting because we have been taking the decimal expansion for granted. And we can use decimal expansion to prove that every point on a line corresponds to a real number. And what do? We just divide the real number into equal lengths, and then each equal length is length 1, and then divide that length 1 into 10 pieces, and we assign first decimal digit, and then 10 pieces again, and then 10 pieces again, and so on and so forth. So we can narrow down to any point on a real line, and that's a decimal expansion. And what this theorem says is the decimal expansion is valid, and the proof is very, very simple. As a matter of fact, the decimal expansion is nothing more than an infinite series given by a, which is an integer part, plus a1 over 10 at the first decimal digit, a2 over 100, plus a3 over 1000, in general an over 10 to the nth power, and that's increasing sequence of partial sums, and that's bounded because it's less than a plus 1. All these decimals, all these will never exceed 1, so it's bounded. So what do we have? We have to have a convergence, so the decimal expansion is always valid. Here's an example, as a matter of fact, the visualization of pi. For example, I just use my Mathematica to plot pi, and then where is it located? Well, as you can see, I just used a real line and then divided into infinitely many pieces with same size. 0 to 1, size 1. 1 to 2, that's size 2. 2 to 3, that's size 1 again. 3 to 4, again size 1. 4 to 5, again size 1. All have size 1. And this point, pi, is located between 3 and 4. Now between 3 and 4, divide it into 10 equal pieces, and then assign the first decimal digit. And it turns out that the pi is located between 3.1 and 3.2. So expand it further, and then divide it into 10 equal pieces again. Turns out that it is located between 3.14 and 3.15. Do it again, and do it again, and so on. And then we have convergence. We have to have convergence because of this theorem. Decimal expansion is valid, and it was based upon monotone convergence theorem.